All right, so I need to give you guys rational functions.
Okay.
So, what's a rational function?
It doesn't.
It's a ratio.
Good. It's primarily is a ratio. So it's a fraction, kind of.
So like 1/x.
Yeah, so an example would be 1/x. So it's a fraction made of
Whole number integers.
kind of, yeah.
Real
So
numbers.
what are the what's the analogy of integers here? Like what are your kind of counting number
1,
like
2,
functions?
3, 4, 5.
Yeah, so
You
1,
have-
2, 3, 4, 5 are your counting numbers,
You can have
right?
Half.
You can
What are
have
your
half.
counting number functions?
F of x equals 1.
Like what are the first functions we taught you guys about?
What was I supposed to be?
Lines, good. Line,
Lines, parabolas,
parabolas,
Yeah.
quadratics are parabolas.
Cubic functions.
Cubics, oh, that sounds like you're listing polynomials to me,
Yeah.
right? So these things are fractions made of polynomials.
Could have been made of monomial.
Nope.
Could certainly be made of monomials, because monomials are polynomials, right?
Wait, I thought polynomials were made of monomials.
They
But
are.
you can't.
They are.
You can't. Right. But a monomial isn't made of polynomials.
No, one
Okay,
is a-
so
but another-
here's what we have so
Monomial
far.
is harder than polynomial.
It's like this.
You have monomials here,
Mhm.
then monomials and some more stuff make polynomials, right? And then polynomials and some more stuff make rational functions.
That's a really good picture, actually.
What is the other stuff? Like, is there another bubble in that?
Yeah, so there's more stuff in here. And Zach just gave us an example of something that's over here that's not in either of those. You guys remember what it was?
1/x.
It's 1/x,
I said it like really loud. So.
right? Because that's x to the -1, which is not a variable to a natural number power, right? It's a variable to an integer power.
Right.
You guys see that?
Yep.
So this guy is not a polynomial, but it is in fact a fraction made of polynomials. In fact, it's a fraction made of monomials. You see that?
Oh,
Oh.
I get it.
Do you get it now?
I do get it.
Whoa.
Okay,
I
cool.
like that.
Do you want to even, I'm going to add something to this picture because it's a fun joke, but it has nothing to do with rational functions. So here's the fun joke.
What are you doing?
That's a cell now.
This is a subset of something called an Euler diagram,
Euler diagram.
right? Diagrams like this are called Euler diagrams.
Why?
What's the name that you guys know for a picture like this?
Avocado.
Freaking.
Avocado.
It's like a brainstorm.
Yeah, so a Venn diagram
Why are you
is
trying
a
more?
bigger
It's
thing.
not.
Why are you expanding that way? Expand to the right. you're
Because I want to use that later, and this isn't related to the lecture.
Why don't you just erase it then when you're done?
Okay, so a Venn diagram is one where the circles might overlap.
Yeah.
An Euler diagram is where the circles all just nest inside each other.
Okay.
Okay.
You
You
guys
call
got
them
it?
Russian dolls.
So yeah, this is a little bit like a Russian doll, right?
So what's on the other side?
Okay, so now let's talk about rational functions.
Okay.
So a rational function, right,
Yeah, I guess that was a joke.
looks like a p of x over a q of x. Oh, what's the
Yeah,
joke?
what's the joke?
The joke is that this diagram sits in there.
What?
What does?
This diagram.
This whole diagram, it's an
Oh.
example of an Euler diagram.
okay.
Oh, that's
Got
kind
it.
of funny.
Right? It,
I was
it
like,
sits
what?
inside itself.
Like, what diagram?
Wow.
Levi got it. Okay, anyway, you have a rational function which is a fraction made of p and q, where p and q are polynomials, right?
Okay.
Poly. And one of our examples of a rational function was 1/x, because 1 is a polynomial, right?
Yeah.
Yeah.
Specifically, it's a monomial, right, because it's a number.
Yeah.
And x is a polynomial by itself,
Okay.
right, because it's x to a natural number power. Guys cool with us? Okay, so this is the form of a rational function, and then there's some interesting stuff that can happen. So, first things first, my rational function, if I set it equal to 0, right?
Yeah.
When is a fraction 0?
Number
One,
0.
Yeah, when the top is 0, right?
Yeah.
So
Where the bottom's essentially.
this is the same thing
Struggling.
as
Struggling here.
p of x is 0 and
Q of X
Is infinity.
no. What do you need to have happen? So what if you
Yeah,
get
Q of
0
X is not-
over 0?
then you get number
Then
5.
it's
Then it's undefined, right?
So Q of X can't be 0.
So you need p of x to be 0 and q of x not to be.
I see what you're saying.
You guys see that?
Yeah.
You guys with me on that?
Yeah.
Okay, so basically there are problems when I have 0 over 0 or when I have,
X over 0.
yeah, some number over 0.
So
You guys see that?
the y-axis is a complete asymptote.
Not necessarily. Let me give you this by example.
Or it never crosses the x-axis because x can't be 0.
Okay, so here's an example. Let's say solve x plus 3 over x minus 2 is 0. Okay, these are going to come up all the time.
You just like
Cool.
When these come up, what do you do?
freak out.
Set X equal
You
minus
just
2.
cross those x's out, man.
So you set
Yeah.
you set both of those things equal to 0.
I would probably just set the top equal to 0.
But you also want to set the bottom equal to 0 so you can say what X can't be.
Okay, so for solving, I'm going to set the top equal to 0. I'm going to get x is minus 3.
Yeah.
And then what I'm going to do to make sure that I'm not disallowed that value is I'm going to take it and I'm going to plug it back into the bottom.
Okay.
I say
Why the bottom?
to make sure it doesn't.
Because to have this thing equal 0, the top has to be 0 and the bottom can't be. You guys see that? So if I plug negative 3 in here, I get negative 5.
Yeah, negative 5.
So I get 0 over negative 5, which is actually 0, like check, cool, good deal. A case in which that doesn't happen would be something like, say I had x minus 2 over x squared minus 4 equals 0.
Exactly.
Right, you'd set the top equal to 0. So you take your x minus 2 is 0. Yeah, or you could factor the bottom. Like that's a good thing to notice. Sometimes, if you have a cubic on the bottom, right, or a quartic on the bottom, you might not be able to factor it easily, but you can always do this, like just take it, plug it back in, see how it works. So, you guys cool with that? So I would get out of this x is 2. I would take x is 2, try to plug it in,
Nope.
get 0 over 0. No, not a thing. So what would the answer to that be?
No solution.
No solution.
Because it's division by 0, there's no answer in the entire universe that would solve that.
Yeah, there is not an answer in the real numbers that would solve that. So over here, my first example there where I had x plus 3 over x minus 2. What do I know that looks like now?
Yo.
It has an asymptote of -3.
Uh-uh.
So across that.
So something happens at -3. What is it?
And it's
It equals 0.
And you plug -3 and you get 0 out, right?
So that's
So I know if I'm over here at -3, there's an intercept,
Yeah.
Oh. okay.
right? This thing crosses the x-axis at -3. You guys all with me on that?
yeah, I see.
And then if you want to figure out what else it looks like, you look at the bottom.
Oh.
When's the bottom 0? 2. So there's major probs at 2.
That's the up.
That's where the asymptote is.
Makes sense.
3 over negative 2 is a y intercept.
Oh, so the asymptote is just
Oh, and
where-
then you could plug 0 in, right?
So the asymptote
So
is
you
just...
get, sorry.
Never mind, go ahead.
Okay, two different thoughts. Zach's first. So the asymptote
Is
is,
wherever the bottom is at 0. Well, I'm wherever the bottom is when you're dividing by 0.
close.
That's where the asymptote
Where X
Yeah,
is.
so,
So wherever the x, whatever the x is, right, I'm trying to...
so hang
Tell
on.
me what I'm trying to say.
Asymptotes are just a little bit subtle. I would love it, like, this would be the thing that would be best in my life. I would absolutely love it.
It's a very nice word.
Thanks, I practiced that one a lot. I would absolutely love it if asymptotes happened exactly when q of x was 0.
Q of x is 0.
Like, this would be the best. It's not true, though. Okay, so then you'd say something like, well, maybe they're like the zeros, right? Maybe you get an asymptote when the bottom's 0 and the top's not. You guys see that? Okay, so maybe you say like, okay, and p of x isn't 0. This is almost true.
Is there one more?
Yeah, you need to reduce it fully first.
Why does that matter?
Let me show you.
All right.
I have that one on the board already. So you could draw this, you could draw a picture of this guy with a graphing calculator. Yes? Or with a couple points. So for instance, if I plug 0 in, which was a good thought, I'd get
3 over negative 1.
let me make totally clear what I'm doing because I'm not. My goal is to graph f of x is x minus plus 3 over x minus 2, right? So I found my intercept, I found my asymptote. My asymptote on this one is quite clear because the top's 5 when x is 2 and the bottom's 0. So 5 split no ways is going to be a problem. You guys all see that? Okay, so I definitely have this asymptote there. And then I need a couple more points just to figure out where things are going. So I might like plug in f of 0. I get 3 over negative 2.
Yeah.
So that's going to be down 1.5.
Yeah.
Okay, so I think this thing probably goes like this.
I see.
So
But,
left.
You guys with me on that? Where does it go as I go this way? Like if I plug in really big negative numbers?
And the other way.
So f of negative big,
Nice.
right, is going to be negative big plus 3 over negative big minus 2.
So you get
So that's basically negative big over negative big, right?
It is positive big.
Big.
Which is positive.
Super big. A 1.
Big over big is probably basically 1.
so it's always gonna be almost
So
a constant.
it's approaching.
It's approaching 1.
So it's approaching 1. So it has what's called a horizontal asymptote.
Do not all of them
That's
have
what I
that? Like function? Like
Not all
rational
functions have horizontal asymptotes.
But functions like that are
Rational functions like this.
Yeah. Do they always have?
Rational functions always have horizontal asymptotes as long as the power on the bottom is at least as big or bigger than the one on the top.
Okay.
Because otherwise it would kind of act like a polynomial and they would point out.
Okay.
Right? Remember, polynomials are rational functions.
Yeah.
Like x squared over 1 is a fraction made of polynomials, right?
Right.
So a parabola is one of these beasts. Parabolas don't have horizontal asymptotes.
Gotcha. Okay.
But as long as the power on the bottom is bigger than or the same as the power on the top, you'll get a horizontal asymptote. Guys with that?
So we don't get one for this.
So we do get one because they're the same.
Same powers.
Right, they're x to the first over x to the first, so I get a horizontal asymptote. And I know actually that that's at 1, because this is 1x over 1x.
It goes
You
to-
can kind of cheat this trick. right? There's a way to look at the coefficients to figure it out. I'll give you that tomorrow.
Thanks.
Right.
For right now, what you can do is cram big numbers in there and just see. So like with this guy, I do, for the other side, I do f of big, right? And so I get big plus 3 over big minus 2.
And it's gonna be good.
Those don't matter. Big over big is,
Like a positive one.
oh, 1 again, right? Cool. And then I should plug in a number over here someplace. Like pick your favorite number over there.
2.
Like,
3.
sure, any of those. As long as it's
4.5.
past 2, you're fine. So I'm going to pick 7.
Really?
10.
Yeah, because that's 10 over 5, which is pretty easy. So that's 2, right? So if I go over 7, I up 2. So I'm looking at this. And I know it tails into 1, and I know it goes to this asymptote, so probably it looks like this.
You are indeed correct.
You guys kind of with me on the picture? And you can check it with a graphing calculator, right?
Yeah.
Okay. So now let me try the other one. So let me see if I can graph g of x is x minus 2 over x squared minus 4.
And this is the one that isn't reduced, right?
Yeah, this one's not reduced right now. It's not maybe obvious that it's not, but it's not reduced right now. So we looked for a 0. We found no solutions, right? So in terms of me getting a picture, what no solutions means is not nothing.
No solutions means it never crosses the x-axis.
Yeah, no solutions actually gives you some information. It tells you that it never crosses the x-axis. You guys see that? This isn't an inconclusive test. This is a nice, definitive, it doesn't do this thing you think it might.
Okay.
Right? So this one specifically does not cross the x-axis. You guys see that? Okay. So, does it have asymptotes?
Yeah. Yes.
A cha, probably.
Like the x-axis.
So you might look at this thing and you say, okay, so when's the bottom 0?
4x is 2.
So you're like, okay, so I'm looking for asymptotes, right?
For when x is 2, everything falls.
So I got x squared minus 4 is 0.
Shit gets bad at x is 0.
So that's x squared is 4. So that's x is
0.
2.
2 or
Negative 2.
Negative 2.
so you would like to do this, where you'd go, okay, 1, 2, and back 1, back 2, right? You'd like to be like, okay, there's an asymptote there, and there's an asymptote here, right? Except
There you go.
2 is also a 0 of the top.
Yeah.
So there can't be an asymptote.
So what you get at 2 isn't number over 0, it's 0 over 0.
Which is undefined.
Which is undefined. So you have to go check if you're reduced. So if you factor this thing,
It'd be like 1 over x minus
you get x minus 2 over x minus 2 times x plus 2.
And you can cancel out the x.
And then you'd say, okay, well, x minus 2 is 1. Or sorry, x minus 2 over x minus 2 is 1, right?
So 1 times x plus 2. 1
1
over,
over x plus 2.
plus 2.
Okay, so you would say this is the same function, right? You'd be like, yo, g of x is 1 over x plus 2, right?
So
Except it's not.
why is that?
Why isn't it?
Because at 2, you have
Because
1.
at 2, you had a problem,
And now you don't.
and now you don't.
Oh,
You guys see that? So it looks exactly the same at everywhere except at x is 2.
Wow.
You guys see that? So I could draw this picture. That's going to look like... Oh, whoops, I erased the wrong one. That's why I put over. You guys see I erased the asymptote that was
Yeah,
at
it's
minus
minus.
2 instead of erasing the one that was at plus 2?
Because it's minus 2. Yeah.
So minus 2 is the real asymptote. The other one is kind of faking me out. So I think, okay, so my picture looks like 1 over x plus 2, which looks, give or take, like this. You guys could do this analysis, just trust me on this one for right now. And then, well, except at, which value did I have to worry about?
2.
Except at 2, which you're not allowed to plug in then.
Also a little bubble.
A local ask.
So that's what's called a hole.
I love holes. Holes are
You
great.
guys see this? So there are three kind of things that happen when either the top or the bottom is 0. Right? If they're both 0, you've got a hole. If the top's 0 and the bottom isn't, then you have an x-intercept. And if the bottom's 0 and the top isn't, you have an asymptote. Right? And if you have a hole, you can also have an asymptote hiding underneath it. That's this. You have to reduce first before you check for asymptotes. You guys cool with this? That's hard. And you guys should, like, this section's tough. Rational functions are hard. But the good news about rational functions being hard is that once you guys are done with this, you'll have a skill that very few people have, which makes you more marketable. Right?
Oh, I like that.
You guys cool with this?
Yeah.
So I realize pre-calculus is hard sometimes, but it's good that pre-calculus is hard because that means it's worth doing.
Yeah.
Right? Easy things don't pay well.
Right.
Cool? Questions, things?
0.
What's an irrational function?
We're not going to talk about them.
Cool.
They're the type of